two types of acetylcholine receptors that are important in human physiology, and those are the nicotinic and the muscarinic cholinergic receptors. You need to be very comfortable in your life talking about receptor types in neuropharmacology. And these are the two most commonly talked about receptors, the cholinergic and the adrenergics. And so today, I'm going to work with you in talking about the importance of the adrenergic receptors, and then we'll talk about some other neurotransmitters along the way. But if you're ever going to talk about autonomics, you're going to talk about medicines and things, you're going to talk about impacts of drugs in various scenarios. The idea here, the functional things are surrounding the adrenergic and the cholinergic receptors will always be part of that conversation, always. So I did the cholinergic stuff with you already. You now have an idea about how cholinergics can explain both activating and inhibiting, or exciting and inhibiting different structures. You have some idea about where these receptors are, and so we're going to do the same thing with some of these. Now, the organization looks like this. We're going to talk about this group of neurotransmitters as a group known as the monoamines. So this is an important biochemistry designation for these chemicals. The monoamines are called monoamine because the chemical itself is produced from a single amino acid. So, as we look down through this list, you can see these are the big four: epinephrine, norepinephrine, serotonin, and dopamine. And three of these, epinephrine, norepinephrine, and dopamine, all come from the same amino acid. And that amino acid is tyrosine. Serotonin comes from the amino acid tryptophan. So collectively, the big four are known as monoamines. Now, there are other ways of designating and separating these chemicals out, but you will always hear them referred to as monoamines. So some people will want to refer to these as the catechols, and these as the indoles or the indolamines and the catecholamines, and there's different language. And those things come up sometimes they don't. But you can always be confident in referring to these big four as the monoamines: epinephrine, norepinephrine, serotonin, and dopamine. Now, these two, the top two, here in my introduction, epinephrine and norepinephrine, are the chemicals in your body that bind to adrenergic receptors. So I'm going to say this several times today. Epinephrine and norepinephrine are adrenergic binding chemicals. Adrenergic, A-D-R-E, N-E-R-G-I-C, adrenergic, A-D-R-E, N-E-R-G-I-C, adrenergic. So, first type of chemical you learned was acetylcholine. You learned it binds to cholinergic receptors. The second type of neurotransmitter molecule you're learning about, epinephrine and norepinephrine, bind to adrenergic receptors. Now, let's do a little better with this as we begin this discussion, epinephrine and norepinephrine. Whenever I taught you a couple of class periods ago about the autonomic nervous system, I said it's divided into two divisions, sympathetic and parasympathetic. Remember? And I had you think about the anatomy of the systems as short and long anatomies affiliated with ganglion or ganglia. So in your model, in your mind, you should have sympathetics as short, long, and parasympathetics as long, short. You should have in your mind that all of the preganglionics, whether it's sympathetic or parasympathetic, use acetylcholine at the ganglion cells. So all the ganglion cells have nicotinic cholinergic receptors on them. you should have in your mind that the postganglionics of the parasympathetics also release acetylcholine. But the receptors on the targets are muscarinic cholinergic, right? The postganglionic sympathetics release norepinephrine. This you also knew. And the norepinephrine binds to the targets, smooth muscle, cardiac muscle, or glands. And those receptors are adrenergic receptors. So there was a reason why I taught you the basic anatomy of the autonomics, because it serves as a good foundation for learning about the two most popular neurotransmitters in human physiology, acetylcholine and norepinephrine. Now, some of you are wondering right now why I keep saying norepinephrine when this picture has epinephrine on it as well. Okay, so I need to address this. This phenomenon of epinephrine and norepinephrine needs to be addressed. So let's do it with what we know already, and I'm going to add a little piece to it on you here. The piece that I'm about to add has been on several pictures that you've seen, but I have not made mention of it yet in order to try to keep things in neat categories for you. But we can no longer leave them in a neat category. It has to be, you have to learn now what this means. Why do the monoamine neurotransmitters include both of these when everything you've learned so far only has norepinephrine acting? It doesn't have epinephrine. Okay, so first thing, these two guys are very closely related in structure, and they bind to the same receptors. So there's nothing new there to say. Epinephrine and norepinephrine bind to adrenergics, and they do it everywhere. The question is, how does this really work in the human body? Okay, so what you know is this. Postganglionic sympathetics release norepinephrine. That you know. And you also know that that is the stress response in the human body. The fight or flight syndrome is a norepinephrine-caused event. These things would include elevations in heart rate, opening the airway, turning off the kidneys and the digestive system, dilating the pupils, the things that happen in order for you to respond to some stressor in your life. The fight or flight syndrome is a norepinephrine-driven syndrome in human physiology. Now, on the images that we looked at before, and I'm not going back in the interest of time, I'm just going to tell you, this chemical right here, as it turns out, is produced by a gland. So it will become the focus of our conversation together about hormones in January. Epinephrine is really, in the human body, a hormone made by the adrenal gland. It's more commonly called adrenaline. Epinephrine is adrenaline, made by an endocrine gland, made by a hormone-producing gland. So that's new. Now, if you go back and look at the image where I taught you the sympathetics, you're going to see something special in the connection there. And in the spring, I'm going to make a big deal about it, because it gives me an opportunity to review sympathetic anatomy with you. Okay, so I added one piece of information there. This is a hormone. Now, from what you learned about acetylcholine, it should be clear in your mind that once a neurotransmitter has bound to its receptor, it will keep doing so unless you get rid of it. So acetylcholinesterase was the example of the postsynaptic enzyme that I taught you that gets rid of the acetylcholine signal. Now, you have to have something like that to get rid of norepinephrine as well. There has to be mechanisms in place in the synapse to stop it. If you keep doing it, if the thing keeps binding to its receptor, then you're going to get some impact that is unpleasant. So today you're going to learn that there are multiple ways to stop these adrenergic signals. okay? And they happen very quickly. So the story of the neurotransmitter is a story of speed. Whenever you want to elevate heart rate, you can do it very quickly because this is a neuroanatomical connection. Neuron to heart. Boom, boom, boom. We're talking milliseconds to get the signal, the norepinephrine signal there. But as it turns out for human survival, oftentimes when you bind a neurotransmitter and then you clear it, or you destroy it in the synapse, the signal will stop with that destruction. But in our lives, survival is not a matter of moments in a lot of cases. Survival becomes a matter of extended periods of time where you need access to elevated heart rates and elevated functional things in the cardiovascular, open airways. Ways of surviving need to last. And so the body knows this. So in addition to the norepinephrine signal that is a neuronal signal, the body also makes a hormone in the adrenal gland at the same time. And that hormone is released and circulates through our bodies. And you cannot get rid of the hormone signal as fast as you can get rid of the neurotransmitter signal. In fact, the kidneys have got to get rid of this stuff. So you have a very fast-acting stress response that involves a monoamine called norepinephrine that binds to an adrenergic receptor. Get the heart rate up. Get the airway open. Get the pupils dilated. Shut the kidneys down. Very quick responses. Redistribute the blood flow. More blood to the muscles. More blood to the heart. Less blood to the gut. These are all things that help us survive. And norepinephrine does that very quickly. But you want this to last. And if it's going to last, you need something in your bloodstream. That's what this stuff does. So these two really constitute the 1-2 punch of the sympathetic nervous system, of the stress response of the human body. Norepinephrine and epinephrine work together. They work in tandem. This one is fast acting. This one is slower and prolonged. They're both considered neurotransmitters when the fact is these are in fact hormone molecules, epinephrine. They got a methyl group on them, that's it. One enzyme in the adrenal gland, and that's the only difference in structure between these two.
You said epinephrine is slower?
Epinephrine is a long-acting, slower and long-acting phenomenon compared to norepinephrine. Epinephrine is slower and long-acting compared to norepinephrine. Okay, I'm going to pick these up as well as we do this because I want you to know something about the rest of these monoamines. Again, these are the big four. They are released by exocytosis, and you know this process using synapsin, calcium channels. They diffuse across the synaptic cleft and interact with specific receptors. Okay, I would like to know some more about that. Okay, so let's take norepinephrine first. This is the adrenergic story. And so I have much to say here. This is a Wade Warren written slide. You guys know that I don't write much. So if I've written it down, this must be really important. There is so much of human physiology. There is so much of human physiology found in this slide to talk about what norepinephrine does. So first, it's in both the peripheral and central nervous systems, the PNS and CNS. Adrenergic receptors are everywhere. Now, in the central nervous system, we'll do this one first, and then I'll go back and forth. In the central nervous system, we know that norepinephrine is involved in mental arousal. So the fact that your cerebral cortex is functioning is an adrenergic phenomenon. Now, in addition, we also know it's not just involved in mental arousal, but it's also involved in mental health. You're going to learn some more about this today, but there's a long list of there's a long list of neurological issues in the human brain that can be explained in part by pathologies involving adrenergic binding. For example, the one that we'll focus in on today is depression. Now, most people think that the depression drugs are all about the neurotransmitter serotonin. The truth is, the original and most powerful antidepressants were adrenergic drugs. And you'll see as I teach you the mechanisms here of destruction of these neurotransmitters why today the focus is in on serotonin for mental depression. But you could certainly make the case that norepinephrine is at least as, and I would argue, more significant in mental condition than serotonin is. So we're going to talk about both of them. I want you to think about norepinephrine is important in your brain for consciousness, for mental health issues. Norepinephrine is an important molecule. In the peripheral nervous system, norepinephrine is primarily interested in causing the events of the sympathetic nervous system. Now that's not going to be good enough. You're going to have to do better than that. So here's the original writing here, the original thoughts here. So I will find adrenergic receptors for norepinephrine and epinephrine in the smooth muscles of my body. Now, and a good anatomy student sees in the smooth muscles of my body, and the good anatomy student says, that's everywhere, right? So when I start anatomy, I do this every year. I say, if you're going to discuss the structure of something hollow in your body, you're going to put smooth muscle there. So for example, if you want to talk about the tubes that go to your lungs, we have to talk about smooth muscle. The smooth muscle is in the walls of the tubes of your lungs. If we want to talk about the digestive system, from the esophagus all the way to the anus, the walls of those structures have smooth muscle in them. Layers of smooth muscle that control all the movement in the digestive system. If we want to talk about the functions of the urogenital system, the tubes that come out of the kidneys that go to your bladder, the walls of the bladder, the tube that comes out of your bladder, the urethra, all of those structures have smooth muscle in their walls. If we want to talk about the connections from the uterus, which is smooth muscle, to the tubes that connect the ovaries to the uterus, all of these tubular systems will have smooth muscle in their walls. If we want to talk about the vas deferens and the ducts of the male reproductive system, we are talking about smooth muscle. Are y'all getting a sense of this? When I say smooth muscle and adrenergic receptors, I said something big for human physiology. Everywhere. The next on the list is cardiac muscle. So you already have a sense about the difference in parasympathetic and sympathetic. So if I said, what does the parasympathetic nervous system do to your heart? What would you say? What's that? It slows the heart down. Yeah. What neurotransmitter does that? Acetylcholine does that. And what is the receptor type on the heart conduction cell, the pacemaker? What is the receptor type there that acetylcholine binds to? It's a muscarinic receptor. And when acetylcholine binds to that muscarinic receptor, it causes an ion channel to open for potassium. And potassium then goes out of the cell, making the interior of the cell more negative. The inhibition. Parasympathetic slow heart rate, and you know how. Norepinephrine speeds heart rate, and it does so with adrenergic receptor binding. I'm going to talk more about it coming up here, but I wanted you to hear them both as I talk about this. Adrenergic receptors are also in the cardiac system. The difference, y'all, in the cardiovascular system is the norepinephrine receptors on the heart are going to influence the rate and the muscle. So the real power in the autonomic nervous system for your heart is in the sympathetic side. The parasympathetics only have access to the rate. They don't have access to the contractility of the muscle. But cardiac muscle cells, along with smooth muscle cells, have adrenergic receptors on them, which means the chemical can act directly on the muscle to cause it to contract. So whenever norepinephrine binds to heart, not only does the heart rate get higher, but the contractility of the muscle becomes more aggressive in your heart. Okay, and then the last one is glands. Now, I'm going to wait on this one because the first chapter of Anatomy and Physiology 2 is the endocrine system. And we will come full circle here as we talk about the way the sympathetic and parasympathetic nervous systems influence glandular secretions all over the body. Okay, so norepinephrine has access to all of this, and so it's going to have access to changes in blood pressure and blood vessels. Now I have here, norepinephrine increases blood pressure and facilitates the constriction of the arteries. Now, this is an overview. Here, I'm going to get more detailed. All right? So, yes, you knew that. That makes perfect sense. I'm going to cause these changes. Blood pressure's going up. I'm going to have widespread vasoconstriction of the blood vessels. But some of you are a little more perceptive than that, I'm hoping. And you're hearing this and you're saying, now wait a minute. During a sympathetic response, you said the heart is going to be, you're going to require more of it. So would it make sense, for example, for the coronary arteries to constrict during a fight or flight response? That doesn't make any sense. Would it, for example, make sense to say that the blood vessels supplying the skeletal muscles in my legs, in my arms, would it make sense for the blood vessels supplying them to constrict? These are muscles that need more oxygen for more energy. So that doesn't make any sense either. So when I say constriction of the arteries, I mean a widespread vasoconstriction, and I'm really thinking more about the gastrointestinal system. Most of the organs of the abdominal and pelvic body cavities are going to constrict. Your body's going to say, during a fight or flight response, shut everything down except the essentials. And the shutting down process is the process of vasoconstriction. This is the way the sympathetic nervous system redistributes blood for human physiology. You guys, now, as you're thinking about this, you know that it makes sense. That during a stress response, I'd want my heart to get more blood and my skeletal muscles to get more blood, not less. So this is general. Now we're going to talk about the specifics, okay? So for adrenergic receptors, there are 5 major types. And I want you to know something about them, okay? So the first one listed here is a B1. This should be the Greek symbol for B. Beta 1. So there are, in the adrenergic receptor world, 2 major superfamilies. Alphas and betas. The beta 1 adrenergic receptor type is the type that we find in the heart. Specifically, the type that we find in the heart rate structures, conduction system. So how does your heart rate go up? By the binding of norepinephrine to the beta-1 adrenergic receptors of the rate-producing cells. That's where you find the beta-1s in the heart.